Hey there, and welcome to this explainer. Okay, so if you've ever stared at a math worksheet full of letters and numbers and just felt this huge wave of anxiety wash over you, I want you to take a deep breath. Right now, you are absolutely not alone. Today, we're going to tackle this together. Think of me as your personal, patient tutor, and we are going to break down polynomials step by step. Seriously, by the end of our time together, what currently looks like a confusing alphabet soup is going to make perfect sense. We're taking it slow, we're looking at the visual patterns first, and we're going to build up your confidence from the ground up. Ready? Let's do this.
So, before we even think about touching a formula, we need to answer a very important question. Why do we even care about polynomials? Well, believe it or not, this exact math is quietly running in the background of your daily life. When a store calculates a complex shopping discount, that's a polynomial. When a surveyor measures an irregularly shaped piece of land, polynomial. When an architect designs the beautiful, sweeping curve of a new building, or even when your phone compresses data to send a photo to your friend, polynomials are doing the heavy lifting. They essentially describe shapes and continuous patterns in the real world. So instead of thinking of them as some abstract, scary rules, think of them as a language we use to draw predictable, beautiful shapes. So let's start translating that language by just looking at shapes and patterns first.
All right, let's look at this comparison. It's like a giant game of spot the difference. On the left, we have our well-behaved polynomials. Notice how clean they look? I mean, yeah, there's a fraction in there, 1/3, but it's just sitting next to a normal, happy x. Now, I want you to gently guide your attention to the right side, the not polynomials. Can you spot the weird stuff? Look closely. We've got an x squared trapped at the bottom of a fraction. We have a -1 hanging out as an exponent. We've got another x acting as a denominator. These visual red flags right here, they completely break the fundamental pattern of the polynomial family.
So, why do those red flags matter? Well, let's look at the logic. A polynomial is just an algebraic expression made up of terms in the form of a times x to the power of n. But here is the absolute golden rule, the one thing you must remember today. That exponent, the n, absolutely must be a whole number. We're talking 0, 1, 2, 3, and so on. No fractions in the exponent, and definitely no negative numbers. Now, why does this rule exist? Because polynomials are meant to be smooth, predictable, continuous curves. Negative or fractional powers, they create sharp breaks, weird asymptotes, or imaginary numbers that completely ruin that smooth pattern. Missing this simple rule is literally the #1 mistake students make in exams. If you see a negative exponent or an x stuck under a fraction bar, you just say, nope, not a polynomial, and move right on.
Okay, so once we know we actually have a polynomial, we give it a name tag based on its degree. And the degree is super simple. It's just the highest power of x you can find anywhere in the expression. It's the boss number. If the highest power is a 1, we call it a linear polynomial because, guess what? It draws a perfectly straight line. If the highest power is a 2, it's quadratic, which draws a nice, smooth U shape. A power of 3 is cubic, creating this cool, swooping S-curve. Hey, even a plain old number like 6 is technically a polynomial. It's a constant polynomial of degree 0 because you can just imagine an invisible x to the power of 0 sitting right next to it. So that degree, it instantly tells you the shape of the graph before you ever pick up a pencil.
Now, if you open a math textbook, you might see something that looks like this. Okay, consider this a brief math jump scare. Do not let this intimidate you. This is just the formal definition of a polynomial of the nth degree. All those a's, they're just regular numbers sitting in front of the variables, and the x's are just counting down in perfectly normal whole numbers. It's the exact same simple pattern we just talked about, just written in a really formal shorthand. Let's move on to some actual numbers so you can see how easy this really is.
Let's tackle an easy example together. I'm going to read the question. Is 2x a polynomial? Okay, what is given? We have the expression 2x. What is asked? We need to verify if it belongs in the polynomial club. Step 1, we look straight at our variable, x. Step 2, we identify its power. Now, there isn't a number explicitly written up there, which means it has an invisible implied power of 1. Step 3, we check our golden rule. Is 1 a whole number? Yes, absolutely. Therefore, 2x is a polynomial, specifically a linear polynomial of degree 1. See? You just applied the rule perfectly.
All right. Now that we can easily spot these things in the wild, let's learn how to actually use them. This brings us to finding the value of a polynomial. Finding a value is really just a fancy mathematical way of saying, hey, let's swap out the letter for a specific number and see what answer pops out. It's exactly like putting a coin into a vending machine and seeing what snack you get. Let's try it.
Time for a medium-leveled challenge. Let's read the question. Find the value of p of x equals x squared minus 2x minus 3 at x equals 1.
So, what is given? We're given our polynomial, and we're given a specific value to plug in, x equals 1. What is asked? We need to find the final calculated value. Step 1, write out the equation clearly. Step 2, everywhere you see an x, replace it with a 1, and always put it in parentheses. So we get 1 squared minus 2 times 1 minus 3. Step 3, calculate carefully. 1 squared is 1. Negative 2 times 1 is negative 2. So we're looking at 1 minus 2 minus 3. Step 4, do the final math, and our answer is negative 4. Now, here is a massive tip. A classic trap in board exams is students dropping negative signs during the substitution step. Always use parentheses. They protect your numbers.
Now look what happens here, because this brilliantly illustrates our next big concept. Let's look at two different outcomes side by side using that exact same equation. On the left side, we substitute x equals 2. When we run the math, 4 minus 4 minus 3, we get negative 3, just a normal, everyday, non-zero number. But look at the right side. When we substitute x equals 3, the math becomes 9 minus 6 minus 3. 9 minus 9 is exactly 0. The whole equation just magically cancels out to nothing. When this happens, we have found something incredibly special.
We call that special magical number a zero of a polynomial. Formally, it just means that if you have a real number, let's call it k, it's a zero if substituting it into your polynomial results in exactly 0, or p of k equals 0. Visually, finding these zeros is basically finding the exact spots where the curve of the graph comes down and touches the flat ground, the x-axis. It is literally one of the most important things you'll ever learn to do in algebra.
Okay, virtual high five right now. You are doing fantastic. You understand the golden rule, you know how to substitute safely, and you know what a zero is. That means we are fully equipped to tackle the final boss, a multi-part, hard-level board exam question. The question wants us to test multiple numbers to prove which ones are the true zeros of our polynomial. We're going to break it down methodically. Let's go.
Part 1 of the exam question. What is given? Our polynomial, x squared minus 2x minus 3. What is asked? Is x equals 3 a 0? Let's trust our steps. Step 1. Substitute 3 in parentheses. We get 3 squared minus 2 times 3 minus 3. Step 2. Multiply it out. 9 minus 6 minus 3. 9 minus 9 is 0. Because our final result is 0, we proudly write, yes, x equals 3 is absolutely a 0 of this polynomial. Boom. First point secured.
Moving to part 2, same given polynomial. The question asks, is x equals negative 1 a 0? Now, actually pause right here. This is exactly where examiners try to trick you. We substitute negative 1 in parentheses. Negative 1 squared, remember, a negative times a negative is a positive, so that becomes a positive 1. Then we have negative 2 times negative 1. That also becomes a positive 2. So our math is 1 plus 2 minus 3. 3 minus 3 is 0. The result is 0, so yes, x equals negative 1 is also a 0. Notice how incredibly careful we were with those negative signs? That right there is how you score top marks. Part 3, the final test. Same given equation. What's asked? Is x equals 2 a 0? Let's test it. Substitute 2. 2 squared is 4. Negative 2 times 2 is negative 4. So we have 4 minus 3. Well, the 4's cancel out, leaving us with negative 3. Is negative 3 0? Nope. Therefore, we confidently state, no, x equals 2 is not a 0. And honestly, just like that, you have completely dismantled a difficult board exam question just by trusting the process and taking it one clear step at a time. Okay, to wrap up everything we've learned today, I want you to take a mental snapshot of this. This is your ultimate 5-point cheat sheet for your exams. Number 1, polynomials only allow whole number powers, no fractions, no negatives in the exponent. Number 2, the degree is literally just the highest power in the expression. Number 3, degrees act as name tags that tell you the shape, like linear for 1, quadratic for 2, and cubic for 3. Number 4, finding a value just means swapping a number for x and doing the math. And number 5, a 0 is that magical, specific number that makes the entire equation collapse exactly to 0. Before we go, I want to leave you with one final surprise trick that's going to save you so much time on your exams. Look at this massive, complicated-looking expression straight out of a textbook. A few minutes ago, this might have caused sheer panic, but right now, can you instantly spot its degree without calculating a single thing? Just scan for the biggest exponent. Boom, there it is, the 6. The degree is 6. You don't need to do any math to know exactly what category this belongs in. See how easy it is once you know the secret language?
The next time you look at a sweeping bridge or the sleek design of a car or a smooth digital photo, remember, you aren't just looking at the world, you are looking at polynomials in action. Keep practicing, trust the patterns, and what will you decode next? See you in the next explainer.